Nature and nature's laws lay hidden night. God said, let Newton be, and all was light. We are here to learn about Newton's laws of motion, which is a natural succession to the study of kinematics, in which we learnt about where an object is lying, or its position, how fast is the object moving, or its velocity, and how quickly is the object changing its velocity, or its acceleration. While we ponder about these problems, it's equally important to study the why aspect of motion. That is, why does motion happen? Why would a stationary object start moving? Or why would a moving object slow down and eventually stop? The answers to these questions might seem simple now, but these very problems had puzzled the scientists the world over for centuries, until Isaac Newton formulated his famous laws of motion. Let us study what these laws are. The statement of Newton's first law of motion is extremely lucid. It says, an object at rest stays at rest, and an object in motion stays in motion with the same velocity unless acted upon by an external unbalanced force. Which means, in the absence of an external unbalanced force, the stationary ball here will never start moving. And if the ball is in motion, it will keep on moving in the same direction with the same speed till the end of the world. Simply put, all the objects in this universe tend to resist a change in the state of motion unless you force them to do it, which is why the law is also called the law of inertia. Now, a lazy cat here is an epitome of the law of inertia. Let us look at a real life manifestation of the first law. If you're standing in a bus that begins to accelerate suddenly, your body tends to fall backwards relative to the bus, wanting to maintain its initial state of motion, as can be seen here. The first law, however, can also seem contrary to some day-to-day observations. For example, any object moving on the ground tends to stop after some time. Now, this is because of the presence of a resistive force called friction between the object and the ground, which means there was always some external unbalanced force acting on the object that caused the change in its state of motion. Still having trouble with Newton's first law? Well, you can always explain it in your own words, just like Kelvin does here. Before we move on to Newton's second law of motion, let us consider a situation. Now, it's not hard to imagine that throwing a tennis ball over a given distance would not be as hard as throwing a 7 kg shot put ball. In other words, if you were to apply the same force on both the balls, the heavier shot put ball would not gain as much velocity as a lighter tennis ball. Which means there is something very intrinsic about the force applied on an object, its mass, and the effect on its velocity. Newton, being the smart guy he was, formulated a law to study all of this. First of all, he defined the physical quantity called linear momentum as a product of mass and velocity. Given two objects with same velocity, the heavier one would have more momentum, and vice versa. Having defined momentum, let us now see how Newton enlightened us with his second law of motion. The statement of Newton's second law of motion says, the rate of change of momentum of a body is directly proportional to the force applied on it, and this change in momentum takes place in the direction of the applied force. Simply put, how quickly the momentum of a body changes depends directly on the force applied on it. Let us consider a body of mass m moving with an initial velocity u. its initial momentum would then be mu. Let us say the velocity of the body changes to v and subsequently the momentum to mv on the application of a force F for a given time t. Now Newton's second law simply says that more the force you apply, more will be the change in momentum of the body in that given time t. And because momentum and force are vectors, the direction of change of momentum would be same as the direction of the applied force. Mathematically, the force applied and the rate of change of momentum, that is, final momentum minus initial momentum upon time t, are directly proportional. Rewriting it, we get this. Now, v minus u upon t is the rate of change of velocity, which we know is also called acceleration. Introducing the proportionality constant k, we get the equation F equal to kma. Interestingly, the SI unit of force, Newton, is so chosen as to make the value of this proportionality constant k equal to 1, as you can see here for yourself. All of this arrangement gives us arguably the most famous equation of classical physics. F equal to ma, or force is equal to mass times acceleration. Simply, more the force you apply on a body, more will be its acceleration. The biggest takeaway from Newton's second law of motion: ma is a force to be reckoned with. Coming to Newton's third law of motion, it says when one body exerts a force on a second body, then the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. If we consider object 1 to be exerting a force F12 on object 2, then object 2 exerts a force F21 on object 1. According to Newton's third law of motion, the magnitude of F12 is equal to F21. The negative sign here denotes the forces act in opposite directions. A common example given to study the third law is a recoil of a gun upon firing. So when the bullet is fired, the gun exerts a force on the bullet, which in turn exerts a reactionary force on the gun, due to which it recoils. An important thing to keep in mind regarding the third law of motion is, although action and reaction forces are equal in magnitude, they act on different objects. You and the elephant here might be applying the same force on each other, but the elephant, in all probability, would be able to pull you towards itself, because the effect of forces of same magnitude on different objects can be entirely different. The summary of Newton's three laws of motion. The first law says objects do not change their state of motion unless forced to do so. In other words, if there is no force applied, there will be no change in velocity, hence there will be no acceleration. The second law gives us a relationship between the force applied on an object and the acceleration produced through the famous equation F equal to ma. The third law simply tells us for every action there is an equal and opposite reaction. That is all in this video tutorial. May the force be with you. Thank you.